All right, so one of the most important aspects in our lives that we probably don't take for granted is petroleum. Okay, we need it. We need petroleum to make plastics. We need petroleum to make our cars go. We need petroleum for our medicines. We need petroleum for transportation. We need petroleum for packaging. We need petroleum to heat our homes when we go a whole blasted week with temperatures under freezing, which has never happened in my entire life. How is petroleum thought to be formed? Plants and animals die and eventually get covered up with sediments. We now know that those sediments better get there pretty quickly, or else they will decompose too quickly and they lose a lot of their energy spread. So basically, we need a lot of animals and plants, mostly plants. Animals are really not going, there's not enough of them. They need to be covered by a flood or by an enormous amount of ash from a volcano, and then they need to be covered over, and intense heat and pressure converts them into petroleum. We used to think at one time that this process took millions and millions of years. And yet, the eruption of Mount St. Helens back in the 1980s proved that it could happen in a very short period of time. They found petroleum being created from Mount St. Helens. Mount St. Helens produced an enormous amount of ash, lava, and it buried. This was a very lush mountain with lots of vegetation, lots of trees. It just flattened it, buried it, turned it into petroleum very, very quickly. It even created its own little Grand Canyon. So we've learned a lot about geology from Mount St. Helens. So before you sit there and going, yay, so we can make petroleum. Mother Nature can still produce petroleum. Yes, she can. Do we really want a bunch of Mount St. Helens erupting throughout the earth in order to make for us more petroleum? So, no, Mount St. Helens altered the ecosystem of the Northwest. Okay? I mean, we do not want that kind of Mother Nature activity. Okay? What gave us all the petroleum that we have today is the fact that the earth was extremely violent at one time and no longer is. Okay? If the earth was to get as violent as it was at one time that created these vast oil fields, then we probably would not be around to enjoy the new petroleum that will be produced. We will be gone. So, is petroleum renewable? Yes. Is it practically speaking renewable? No. About 5,000 years ago, we started using petroleum in one way or the other. Ancient Middle Easterners collected the petroleum that seeped from the ground and used it to waterproof ships and canals and pave roads. Those of you who are familiar with the Bible, you'll be familiar with the story of Noah, right? Who was asked to build an ark made of gopher wood. And he was to apply pitch, that's petroleum, inside and outside, in order to make the seams between the wood planks, that is a lot of pitch, in order to make the seams in between the wood planks waterproof. So, yeah, even the Bible talks about petroleum. About 1000 AD, Arabs had developed a way of processing oil to make kerosene for lighting. At the same time, the Chinese were extracting oil from wells. Marco Polo tells us about that. As far as modern use of petroleum, 1859, a well was sunk in the U.S., and we started using petroleum that way. So when we talk about petroleum, we talk about fossil fuels. What are fossil fuels? Petroleum, natural gas, and coal. All of that stuff was made by enormous amounts of mostly plant matter. Okay, they call it fossil fuels because they came from ancient plant material. Where do fossil fuels originate from? The biomolecules of prehistoric animal and plant life. Mostly plant, but I'm sure that any animal that got trapped under all that debris also became petroleum as well. What is one way of thinking of the concept of energy being released from fossil fuels? Ever had a vermin problem in your home? A mouse problem? Happened to us. We had never had a problem before. And then on one particularly cold winter several years ago, a family of mice decided to move in. I don't know how they got in, but they moved in. And they were fruitful and multiplied. And they turned our whole world upside down. And my wife did not like the little sticky pads where they crawl on there and they can't get out, because you know how they die, right? They die of malnutrition, of dehydration, which is, a pretty nasty way to die. So my wife has a great big heart. I don't have a big heart like that, but my wife does. So she made me use mouse traps. And I still have the scars for using mouse traps. Who's ever been hit with a mouse trap? Oh my gosh. Painful, isn't it? Okay, so what do? You have to actually apply energy in order to pull back on the trap, on that spring, right? And then you use the little wire to hold it straight so that it's ready. You are storing energy, okay? You're going to kill the mouse by taking your energy and storing it in that mouse trap. And when the little mouse, when Mickey comes in and starts chewing on the cheese and triggers the trap, then all of your energy that you stored back a day ago, 2 days ago, 3 days ago, comes out on Mickey's head. Okay? My wife preferred that because it was a very quick and honorable death. He went out the way he probably would have wanted to go out eating something yummy. Okay? All right, so the two targets we need to hit today are: I can distinguish an exothermic reaction from an endothermic reaction, and if given an energy diagram, I can identify the reactants, products, activation energy, heat lost or gained, and whether it is an exo or endothermic reaction. All right.
I have a certain fondness for saying that everything is chemicals. Mostly, this is because I'm tired of people complaining about all the chemicals that they're exposed to, when literally everything you have ever been exposed to, including the most organically grown lettuce, is composed entirely of chemicals. But when I say everything is chemicals, I am in fact wrong. There are quite a lot of things that aren't chemicals: sound, heat, laser beams, the existential concept of selfness, rainbows. All of those things are things. And all of those things, and also all other things, are in fact, oh God, this is weird, but it's true, they're all the same thing: energy. Everything is energy.
Everything is energy. I even found out while we were so bored at home that Hank Green is a brony. Yes, he is a brony. He has, you need to get on YouTube and watch this video of him singing about My Little Pony. Oh my goodness. I'm afraid that my respect for him went down a little bit. Of course, what? Oh, all the way down? Sorry. Jeff, looks like Jeff is happy. I don't get it. I don't get it. How is chemical energy released? Well, when atoms are pulled apart from their compound formed and then reformed into new compounds, that is when energy is released. And sometimes a net amount of energy, more energy, needs to be absorbed than released in order for that to happen. So during the breaking and forming of bonds during a chemical reaction, here's a good example. We did this back in the middle of last semester. Remember creating hydrogen gas by reacting zinc with hydrochloric acid? And then using some of that hydrogen gas along with some oxygen gas that was liberated from the decomposition of hydrogen peroxide to make the fuel for our rockets. I think was it Chance that won the competition? Yeah. Yes, he and Jeffrey were able to get the rockets to go the farthest, right? That's how did you? Energy had to be released in order for that rocket to fly across the room. Energy had to be released. So you used the energy that was stored in hydrogen and oxygen, so that when those atoms were pulled apart and reformed in the form of water, energy was released. What do we call the release of energy? Exothermic. Exothermic reaction. Exothermic reaction. All right. So here is an exothermic reaction that we dealt with in the last couple weeks with all these low temperatures. Natural gas, oxygen that can be found in the air, gets disassembled into its constituent points, atoms, and then reassembled as carbon dioxide and water. Notice that methane had this much energy, and now carbon dioxide and water have this much energy. Something happened. Something happened. Carbon dioxide and water do not need as much energy to exist as does methane and oxygen. So since they don't need as much energy, then we have energy that's no longer needed. That energy is used by us in order to heat our homes. So this is an exothermic reaction because the products have less energy in them than the reactants. What do we call the fact that when we are heating our homes, we need a little pilot light to pass the gas through in order to ignite the gas? Or in our cars, what do we call the little spark plugs giving energy in order to make the gasoline ignite and produce the energy needed to make our cars go? What do we call the energy just needed just to get it started? Activation energy. Activation energy. A good example of an exothermic reaction is quite simply going up to, and this is, for most of us, this is irresistible. Go up to a mountaintop or a hill, finding a rock, and what do you have to do with the rock? Throw it. You have to. You have to. Kick it, throw it, whatever. You want to see the fun and mayhem that is produced as that rock comes tumbling down. But did you have to keep kicking it downhill? No. One little kick got it downhill. In a way, that rock had a lot of energy in it being on top of that hill. Maybe somebody picked it up from the bottom of the hill and carried it up. They used energy in order to get up there. The higher you are from the center of the earth, the more energy you will have. So when you kicked that rock down to the bottom of the hill, it lost energy. It lost energy. This is an example of an exothermic reaction. The rock being closer to the center of the earth now has less energy than it did when it was up on top of the mountain. And all it took was a kick from you. What kind of reaction is one that takes in energy? Endo. Remember, it's really easy to remember the difference because in biology, insects have skeletons that are insects have endoskeletons, exoskeletons. Yes. So skeletons that are found outside of the body are exo. Think of exo meaning outside. Okay? We have endoskeletons. Our skeletons are found inside our bodies. So, an example of an endoskeleton is perhaps you are in a very weird mood and you are going to climb a mountain and you find a stone at the bottom of the mountain and you want to bring it up to the top of the mountain. What are you going to have to do every step of the way? You're going to have to keep adding energy to it. So every step as you go up the mountain, you're adding energy to that stone. And then you go up to the top of the mountain and place it on the top of the mountain in order to give Asher a chance to kick it all the way back down. Okay, so picking up a stone or pushing a stone or Carrying a stone up a mountain is an example of an endothermic reaction. Folks, no one explains it better than these group of Indian people did. Indian from India, and they are awesome.
Reaction. When calcium oxide is mixed with water, a lot of heat is produced. When coal is burnt again, a lot of heat is produced. Similarly, on burning natural gas, a lot of heat is evolved. Respiration. Glucose combines with oxygen in the cells of our body to form carbon dioxide and water, along with the production of energy. Respiration is an exothermic process because energy is produced during this process. The decomposition of vegetable matter into compost is also an example of exothermic reaction.
Miss Adler is the compost queen.
Endothermic reaction. There are some reactions which take place when energy is supplied.
What is wrong with this person's pants? Look at this. Is this all the rage in India?
Example, when ferrous sulfate is heated, ferric oxide.
Okay, so this sagging fellow is adding energy. If he doesn't add energy, this doesn't happen.
Sulfur dioxide and sulfur trioxide are formed. When electric current is passed through the water, it decomposes to form hydrogen and oxygen gas. Silver chloride breaks up into silver and chlorine in the presence of sunlight.
Yes, it's happening in the Alps.
In all these reactions, energy, either in the form of heat, electricity, or light, is required to break the reactants.
They're kind of silly, but I like them. I like those videos. All right, so I need to explain to you how to show this, how to demonstrate this graphically. So we're going to make two different graphs here. We're going to start out with a reactance line. So that's where that's how much energy the reactants have. The reactants are going to have 40 joules of energy. Joules of energy. Now, we're going to take off upstairs. That is how much energy is needed to disassemble the reactants. Okay, what do we call the energy needed to disassemble the reactants? Ionization. Ionization energy is the energy required to strip away the outermost electron. Activation energy is it. So from here to here is what we call the activation energy. So it's kind of like playing, having your little brother, little sister take apart your Lego device that you built back 5 years ago and reassemble it in some other way. So you find it, you go, oh my gosh, I'm going to kill him. But in order to reassemble it back into a Star Destroyer, or whatever it was you built, you're going to have to take apart all the pieces, right? That's activation energy. Now, the graph is going to go down here to produce products. Or stay up here to produce products. The difference between the amount of energy the reactants have and the amount of energy the products have is called the heat of reaction. Okay, one of these graphs shows an exothermic reaction. The other one shows an endothermic reaction. Who can tell me which one is which and why? You want to try it? Go ahead.
I'm going to say that the first one is endo because the heat of reaction happens before the product. And I'm going to say exo is the second one because heat reaction happens after the product.
Interesting. Okay. Hold on to that. Let me give you an example, an analogy. And then after that, I'll let you either affirm that that's the answer you're going to come up with or change your mind. Okay? Jeff, let me give this analogy, and if he can't nail it, then you can. All right, so two situations. Situation A. You go to the mall, and the Westtown Mall is a different kind of mall. It's not like this mall. It's different. Okay, so you go to the mall, and there you so you're gonna have to use up a little bit of money in order just to get you to Knoxville, right? Okay. There you open up your guitar case. Let's make believe. Do you play a guitar? No. Okay, you do now. Okay. You take out your guitar case and you take out your guitar and you start playing the guitar and singing there. That's why I had to tell you it was a different kind of mall. I think that the people in the little Segways would come and arrest you if you were to do that. But in this mall, you can have artists out there. So you're singing and you're having a good time, and people are dropping coins in your guitar case. So at the end of the day, you count up your money, and you have gained money. Okay, you got money. How much money doesn't really matter, but you got money. So you go home and you have more money than you used to have. Okay? Second situation. You go to Westtown Mall without your guitar, and you go to the Cheesecake Factory, and you buy a burger and a drink and a cheesecake, and then you go home. Okay? Which one's exo, which one's endo?
The guitar one is endo.
Very good. Why?
Because it's taking more energy to get a reaction.
It's taken in energy in order for the reaction to occur. Okay, let me rephrase that. All right, so you had, let's say, $40, and you made $10. So at the end, when you're the product, you have $10 more. So you have $50. Okay? And the other analogy, you had $40 and you spent $20 at Cheesecake Factory, which, by the way, folks, I went there. That is very expensive restaurant. Okay, don't give me that. I don't know how the people in Big Bang Theory can go there every day, unless the fact, they're all single and they make probably good money being professors at the college. That is a very expensive place. Okay? So, $20 is probably a cheap meal at Cheesecake, right? So you now have less. You have $40, now you only have $20 left. Okay? Show me exothermic, show me endothermic on the board.
Okay. Endothermic is with the guitar one, so that's the second one.
Very good. So, here he is, and he goes to Westtown Mall, so he does have to spend a little bit of money just to get to the mall, and then he comes back home, and when he comes back home, he has more money. He gained $10. So, we say that endothermic is an uphill reaction. You gain energy. Money goes in. Energy goes in. Here, he had $40. He used a little bit of money to go to the bank, and net result is when he comes back, he has $20 less. What happened? His checking account went downhill, didn't it? He lost money. The energy went out. The energy went out. The money went out. Very good. Very good. Any questions about these two types of energy diagrams? You will have to identify these things and tell me whether it's exo or endo, and tell me how much energy is lost or gained. So if it goes down, energy is lost. If it goes up, energy is, and what you're looking for is the difference between the products and the reactants, not this. That activation energy is really of no use to us. So, what are energy conversions? What are energy conversions? Let's stop right there.